All right, good evening, guys. Tonight, I want to prove the two-fund theorem. And the two-fund theorem states that all people, no matter what their actual preferences, should buy the exact same portfolio of assets. They might buy more or less of the risky and the riskless asset, but they will buy, when they buy risky assets, they should buy the exact same bundle, all of them. And this is going to go over a lot of the basic techniques that I think we're going to need to know for passing the test, and so that's good. So here's the setup. We have agents who have wealth, and their wealth comes from wages, YT, or investments. And how do they get investments? That's complicated, of course. They can buy either risky assets, so stocks, or riskless assets. Let's say put it in the bank and just get an interest, a deposit. So this theta t will be the amount that they invest in each risky stock, and then everything they don't invest in risky stocks, they're going to invest into their bank account. So that's going to be this, W minus theta t transpose times 1, and that looks like this. That's going to end up being the sum of the thetas minus W. So it's all the money left over. How much do they make? The deposit gets you R dt for sure, and then the risky asset has a return of dp over p equals d mu t dt plus sigma t dzt. So it's a geometric Brownian motion. And therefore we can say that the price of risk is lambda, the price of risk lambda is equal to the inverse of the variance covariance matrix sigma times the quantity mu t minus rt. And that makes sense. Mu t should always be larger than RT because you're taking on risk to do that, to buy that stock, hold it. And then how much risk? Well, it's the inverse of this matrix. So that is lambda. So how do you start a problem like this? We start by figuring out how much money does the person have? What is their wealth? So dW. And what is their wealth? Well, it's going to be first the amount of riskless asset they hold. So WT minus theta t transpose 1, and then R dt. I guess RT dt is better. We don't need to assume that it's always the same. And then they also get money from holding risky assets. So that's theta t times the amount they get from that, mu t dt plus theta t dzt. Plus they have their wages, and they lose as much as they consume, and that's also over time. So that should be the total wealth of the agent. And so we can reorganize that to be into dt and dz parts. So let's write this like this. The risk-free part, theta t transpose 1, that's a 1. RT dt, whoops, no dt, we're holding off. RT plus theta t mu t dt. Geez, I am not doing well at this. Theta t mu t. Theta t mu t, and then all of this will be times dt plus yt minus ct dt plus the stochastic part, theta t sigma t dzt. What we actually want is this in terms of pi. So what is pi? Let's define a new variable, pi, and we will define pi to be the proportion of wealth that they allot to each risky asset. So it's a fraction of their wealth invested in each asset. And then 1 minus pi will simply be the amount invested in each riskless asset. And this will be t. So to get this value in our dW, let's multiply everything by W over W. W over W, and then that will give us hopefully what we want. T1 RT plus theta t mu t dt plus w over w yt minus ct dt plus w over w theta t sigma t dzt. So in the first term, we're going to end up, factoring it in. We're going to have a w on the outside, and then we'll send in the 1 over w. So we'll get 1 minus pi t rt. I don't have enough parentheses. Plus pi t mu t dt. This w we're not going to use, so we'll just throw it away. Ct dt plus wt pi t sigma t dzt. And that is going to be our wealth process, dw. So I'll stop this one here. I'll maybe try to make them shorter with a couple more chunks. In the next video, we're going to derive the Bellman equation. We're going to start deriving the Bellman equation. I think that one's going to take multiple videos. So I'll see you then.